By the end of World War II, Great Britain had built up an incredibly powerful and technologically advanced aviation industry. But there was a catch. For the previous 5 years, British engineers had barely even thought about designing commercial airliners. All their resources were poured into the war effort. Meanwhile, as the fighting raged on, air transport rapidly proved its worth. That small handful of commercial aircraft Britain had back in 1939 eventually snowballed into a massive fleet of military transports. Ultimately, this airlift capability played a vital role in the defeat of Germany and Japan. With a few exceptions, the growing demand for transport aircraft was met by the United States aviation industry. This was under a prior agreement between the Allies. Thanks to this division of labor, American manufacturers ended up in a dominant position. They were ready to meet the massive global demand for new airliners the moment the war ended. This left British aircraft manufacturers in a tough spot. On one hand, they were held back by a 5-year gap in developing dedicated transport aircraft. On the other hand, the British held a significant advantage. They had cutting-edge gas turbine engines. When it came to this advanced technology, Great Britain was comfortably ahead of every other country in the world at the time. This included the United States. It is worth noting that the very first jet engines were designed exclusively for military use. In fact, American experts of the time considered them entirely useless for commercial aviation. The main reason was that these power plants burned a massive amount of fuel. This made commercial operations completely uneconomical. Over in Great Britain, however, a few forward-thinking designers had a totally different take on the matter. At first, their opinions were split. Some engineers favored pure turbojets. Meanwhile, others put their money on gas turbines driving conventional propellers, in other words, turboprops. Because the turboprop promised major fuel savings, most experts agreed it was a much better fit for commercial aviation. Sure, these aircraft would not be able to reach the high speeds that pure turbojets could deliver, but fuel efficiency seemed like the bigger priority back then. As we know today, history ultimately settled the debate. Turbojet technology won out. Jet-powered airliners became the undisputed kings of the sky starting in the 1960s. Meanwhile, turboprops took a back seat. They carved out a niche for themselves in regional transport. But the ongoing evolution of aviation ended up validating both engineering camps. By the 1970s, turbofan engines began to dominate commercial aviation. At their core, these were the perfect, logical blend of the best features from both turbojet and turboprop designs. Even though Great Britain could not spare the manufacturing capacity to build commercial transports at the height of the war, the government was still conducting in-depth studies into the future of its civil aviation. As early as 1942, the British government established a special group of experts. This group would go down in history as the Brabazon Committee. The job of this committee was to define the requirements for various types of airliners. These were the airliners the country would need once peacetime arrived. One of the primary recommendations to come from this committee was a project known as the Brabazon Type 2. This was an aircraft designed to carry 24 passengers. This made it ideal for short to medium-haul European routes. 2 categories were proposed for this new airliner. The first would be powered by conventional piston engines, and the second would be powered by cutting-edge turboprops. Vickers and Armstrong Whitworth stepped up to pitch designs specifically for that second turboprop category. As a result of their initiative, by the spring of 1946, the Ministry of Supply officially ordered 2 prototypes from each company. Ultimately, this massive effort resulted in 2 legendary aircraft. These were the Vickers Viscount and the Armstrong Whitworth Apollo. Armstrong Whitworth started working on a new passenger airliner. It was designed to comfortably carry 24 to 30 passengers. The designers were given a clear objective. The aircraft had to deliver a range of 1,000 miles. It also had to maintain a cruise speed of 300 miles per hour. Back then, gas turbines were just making their debut in commercial aviation. Because of this, engineers were locked in heated debates over which type of engine compressor was best. On one hand, you had centrifugal flow compressors. They were heavy and rugged, but incredibly reliable. They were already proving successful on engines like the Rolls-Royce Derwent and the de Havilland Ghost. On the other hand, brand new axial-flow compressors were entering the scene. They were still in their infancy. However, they promised much higher efficiency down the line. When it came to early turboprops, the field was basically split between 2 engine architectures. You had the Rolls-Royce Dart with its classic centrifugal flow compressor. Then there was the Armstrong Mamba. This engine featured a long and incredibly slender axial compressor. On paper, the Mamba held massive potential for future development. So it is no surprise that Armstrong Whitworth chose the Mamba for their new AW.55 airliner. This choice was driven by corporate ties to their sister company. Meanwhile, their rivals at Vickers played it safe. They bet on the proven Dart engines for their ambitious Viscount project. Time would ultimately tell who made the right call. The project from Armstrong Whitworth was dubbed the Apollo. It proved to be a commercial failure. The main culprit was that troublesome Mamba engine. The Viscount, however, became a massive commercial success. This was largely thanks to the phenomenal reliability of its Dart engines. Interestingly enough, in the world of pure turbojets, the story played out in exactly the opposite way. For instance, the early Comet airliners first flew with centrifugal compressors, but those were quickly eclipsed by axial-flow engines. Eventually, the newer technology completely pushed its outdated centrifugal competitors right out of the market. As for the Mamba engines initially mounted on the Apollo, their specs looked great on paper. The design called for 1,010 shaft horsepower on takeoff. It also provided an additional 307 pounds of residual jet thrust. Engineers hoped that by the time the airliner reached full-scale production, they could bump that output. They aimed for 1,270 shaft horsepower, but reality turned out to be much harsher. By the time the Apollo made its maiden flight, the Mamba engines were barely cranking out 800 shaft horsepower. This was despite them weighing in at 780 pounds dry. The main selling point of the engine, however, was its incredibly small frontal area. It measured just 31 inches in diameter. Here is how it worked. Air flowed in through an annular intake. This intake was wrapped right around the reduction gearbox. From there, it passed through a 10-stage compressor. Then it moved into 6 combustion chambers, spun a 2-stage turbine, and exhausted out the nozzle. The reduction gearbox took the massive 15,000 revolutions per minute of the turbine. It stepped it down to a much more manageable 1,450 revolutions per minute at the propeller. This ambitious engine was first fired up on a test stand back in April 1946. Later, it was mounted in the nose of an Avro Lancaster testbed. This testbed made its first flight in the fall of 1947. The following year, the Mamba turboprop powered the Bolton Paul Balliol trainer. Shortly after, it was flight tested on aircraft like the Avro Athena and the Handley Page Marathon. In early 1948, the engine passed its official 150-hour civil and military certification tests. By the fall, it endured a rigorous 500 hours of continuous endurance testing overseen by aviation authorities. These early trials seemed to prove its reliability, pointing to a bright future for the engine, but it just was not meant to be. As soon as the Mamba was installed on the Apollo airliner, a host of technical issues cropped up. Unfortunately, engineers never managed to iron out most of these critical flaws during the short lifespan of the aircraft. If you look at the early design drawings, you will see an airplane with a wingspan of 92 feet. The fuselage, meanwhile, was relatively short, coming in at just 64.5 feet long. But the design evolved. During the later design phases, they stretched the fuselage to 68 feet. And by the time it reached the final production version, the aircraft had grown again, stretching to 71.5 feet. In 1946, alongside the development of the baseline AW.55 airliner powered by Mamba turboprops, designers pitched another ambitious concept. This was a turbojet-powered variant designated the AW.55 Mark II. The plan was to equip it with 4 Rolls-Royce Derwent 5 turbojets, each producing an impressive 3,500 pounds of static thrust. With this power plant, the aircraft was projected to have a cruising speed of 375 miles per hour at an altitude of 25,000 feet. Meanwhile, its maximum unrefueled range was estimated at 1,000 miles. The fuselage was intended to remain identical to the Mark I. The wing, however, was modified with a slightly shorter span, and the landing gear was completely redesigned to handle the new configuration. Engineers also proposed a high-density version of the airliner. This involved adding a 6-foot, 8-inch fuselage plug, bumping the capacity to 45 or more passengers. Unfortunately, both this stretched variant and the turbojet model never made it off the drawing board. At the same time, the developers realized the airline industry was somewhat resistant to rapid change. Many operators at the time were still skeptical of the new gas turbines, preferring the reliability of proven piston engines. A conventional version of the AW55 was pitched specifically for these conservative customers. This model was offered with a choice of classic power plants, either the Rolls-Royce Merlin 35 or the American Pratt & Whitney R1830 Twin Wasp. As the AW55 finalized development, finding the perfect name became a priority. Initially, they considered the name Achilles, then Avon, before ultimately settling on the strong, recognizable name Apollo. The maximum takeoff weight for the Apollo was around 45,000 pounds. Depending on the cabin layout, it could comfortably seat between 26 and 31 passengers. For its time, this aircraft boasted some truly advanced technology. For instance, both the cockpit and the passenger cabin were fully pressurized and air-conditioned. To deal with in-flight icing, engineers included a dedicated thermal desing system for the wings and tail. On top of that, the airliner featured constant speed propellers that automatically adjusted their blade pitch. They also included a reverse pitch function for more effective braking on landing. Looking at the cross-section, the fuselage of the Apollo was perfectly circular with an internal diameter of 10 feet and 2 inches. The structure was designed to handle a pressure differential of 5.5 psi. Simply put, this meant that when the airplane climbed to its cruising altitude of 25,000 feet, the pressurization system maintained a perfectly comfortable 8,000-foot cabin altitude. The fuselage skin itself was built from lightweight yet highly durable duralumin. To make the airframe even more robust, special stiffeners were riveted directly to the inside of the skin. The wing design of the aircraft was also incredibly interesting. It was built around a lightweight framework assembled from sheet metal. The outer skin was attached over this. For extra rigidity, it was reinforced internally with a hidden corrugated layer. This allowed the wing to handle heavy, in-flight structural loads. The fuel system consisted of 6 tanks safely tucked away inside the wings. There were 3 tanks on each side. On the trailing edge, taking up all the space from the wing roots out to the ailerons, they installed Fowler flaps to provide better lift control. To keep the horizontal stabilizer out of the turbulent airflow coming off the wings, it was mounted high on the tail. The elevator also featured a clever aerodynamic balancing system. Essentially, this internal balance panel hidden inside the tail section used air pressure to reduce control forces for the pilots flying the multi-ton aircraft. By the way, the designers had already successfully tested similar technology on their futuristic AW52 flying wing project. The rudder has an interesting story of its own. Originally, engineers planned a 2-piece split rudder design. The idea was that the primary section would operate normally. The secondary section would only kick in during aggressive maneuvers. This was done to give the pilots enough control over the aircraft even in a worst-case scenario. One example would be an asymmetric thrust situation where they suddenly lost both engines on the same wing. For the Apollo, this was a highly relevant issue. Its engines were incredibly powerful and mounted quite far outboard from the center line. In practice, though, they had to scrap this complex rudder design. The exact same fate met another ambitious concept. This was a gust alleviation system. It was supposed to automatically deflect both ailerons upward during heavy turbulence to shed excess load off the wings. However, this tech never actually made it onto the final production airliner. As for the landing gear, the main struts were equipped with dual wheels. Interestingly, the retraction mechanism looked more like something you would see on a military fighter. Instead of folding into the engine nacelles like on most airliners, the struts retracted inward toward the center line of the fuselage. The engineers had to go this route because of the Mamba turboprops chosen for the aircraft. They had such a slim profile that the wheels simply would not fit inside the nacelles. The nose gear, on the other hand, used a much more conventional setup. It just folded straight back into the fuselage. In their early promotional materials, the designers of the Apollo heavily touted a unique landing gear design featuring long travel shock absorbers. They claimed this would allow pilots to land the aircraft without needing to fly a perfect approach. At the same time, it would still guarantee a smooth touchdown. More than likely, the engineering team was inspired by early experiments with another well-known British aircraft, the Albemarle. However, despite the bold promises, this intriguing concept never saw any further development. Construction of the Apollo prototypes began in early 1948. Engineers built 2 complete flying airframes plus a third fuselage dedicated entirely to ground testing. At the time, pressurized cabins were still a relatively new concept in Great Britain. Because of this, testing on this extra airframe focused heavily on how well it could handle pressurization cycles. This test fuselage occupied the only available test rig at the Baginton plant. While this delayed the assembly of the second flying prototype, the engineering team considered pressure testing so critical that they intentionally prioritized it. With traditional compressed air testing, there was always a massive risk. The fuselage could explode under the extreme load. A catastrophic failure would not just destroy the test article, it would obliterate any valuable evidence showing exactly where the initial crack or structural failure originated. That exact problem led the designers to a brilliant solution. They began running the pressure tests inside a massive water tank. The concept was simple but incredibly effective. Since water is practically incompressible unlike air, it does not store up destructive potential energy. If the fuselage skin suddenly ruptured, it would not result in a catastrophic explosive decompression. The first test article for the Apollo was its forward fuselage section. It was considered the most vulnerable area because of its complex geometry and the extensive glazing around the cockpit. Finding a water tank large enough for the job was no easy task, but the team at Baginton got creative. Someone remembered an old emergency hospital. It was built during World War II as a reinforced concrete bunker. After the war, the bunker had been buried underground. They excavated it for these tests, removed the roof, and completely waterproofed the walls. The result was the perfect test tank. It easily accommodated a 22-foot-long fuselage section and held a staggering 27,000 gallons of water. To pump that much water into the fuselage, they needed a high-volume, steady flow. The standard municipal water supply just was not going to cut it, so the engineers set up a dedicated header tank on the roof of an adjacent factory building. This provided them with perfectly stable water pressure. During the initial tests, the internal pressure of the fuselage was gradually increased to its maximum design load. This target was 1/3 higher than the normal operating pressure. For the Apollo, this meant hitting 7.33 pounds per square inch. Under strict testing guidelines, the structure had to sustain that pressure for 2.5 minutes. It had to do this without any yielding or permanent deformation of the metal. The airframe passed this standard with ease. Even better, during the next stage of testing, they pushed the pressure all the way up to 13 pounds per square inch. That was nearly double the standard operating limit. Yet the fuselage remained completely intact without any structural damage. It is widely believed that these tests at Baginton were the very first in aviation history to use a water tank for pressurization testing. But here is an interesting fact. At the time, this innovative method was not being used to study metal fatigue. This is the kind of fatigue that builds up from repeated pressurization cycles during actual flights. In reality, that aspect of pressurized flight was not even considered a serious issue until 1954. It took the tragic crashes of the Comet jetliners to finally bring the dangers of metal fatigue to the forefront of the aviation industry. Much later, when the Apollo prototype was finally retired from flying, it was sent back to Baginton. There, the aircraft was dismantled and used for a series of new cyclic pressurization tests. This was a major part of a broader research program into aircraft metal fatigue. During these rigorous tests, the fuselage of the Apollo successfully endured 38,000 pressurization cycles. To give you an idea of the scale, that is equivalent to at least 60,000 flight hours. This translates to well over 20 years of continuous airline service. This was stunning, undeniable proof of just how reliable the design of the aircraft really was. By March 1949, the Apollo prototype, painted in Royal Air Force colors, was ready for its initial engine ground runs. After standard runway checks and high-speed taxi testing, the aircraft finally made its maiden flight on April 10th of that same year. However, serious problems surfaced almost immediately. The biggest headache for the engineering team turned out to be the Mamba turboprops. These engines were still highly unrefined and underdeveloped at the time. The development team quickly learned a harsh lesson. Just because an engine runs flawlessly on a test stand does not guarantee it will perform reliably in the air. To prevent the turbines from melting due to excessively high exhaust gas temperatures, the output of each engine had to be restricted to just 800 shaft horsepower. On top of everything else, the Mamba engines frequently suffered from compressor stalls. This led to highly unstable operation. As a result, most of the early test flights of the Apollo turned into a constant struggle with the hardware. The test pilots and engineers tried everything they could to get the power plants running properly. But despite their best efforts, these and other chronic issues with the Mamba turboprops were never fully resolved. This ultimately ruined the reputation of the aircraft for good. It later turned out that these troubled engines only managed to produce their promised 1,000 shaft horsepower for a very brief period. And even then, this did not happen until the very end of the flight test program. That success was short-lived, however. Due to constant compressor blade failures, the engines had to be derated back down to 970 shaft horsepower. Engineers calculated what would happen if they had actually managed to mature the engines and squeeze 1,270 shaft horsepower out of them. The cruise speed of the Apollo would have reached 280 miles per hour, with a range of 1,260 miles. For comparison, with the 1,000 horsepower limitation, those numbers were much more modest. Airspeed did not exceed 270 miles per hour, and the range was capped at 1,130 miles. But there was a catch. More powerful engines on takeoff would have significantly increased the minimum control speed. This speed was required to safely handle the aircraft in the event of an engine failure. It also would have reduced its overall stability. Why? It all came down to the design. Because of their considerable length, the Mamba engines placed the propellers far forward. They were positioned well ahead of the center of gravity of the aircraft. This created a noticeable destabilizing effect in flight. The higher the power setting, the more this effect was felt on the flight controls. However, the worries of the designers were not limited to the power plants. The airframe itself threw a few nasty surprises their way. The main problem was the rather short fuselage. It did not provide a long enough moment arm for solid directional control. Because of this, the aircraft suffered from instability, constantly wandering in both pitch and yaw. On top of that, the elevator lacked the surface area needed for adequate pitch control. Furthermore, the rudder pedal forces were excessively heavy. Engineers managed to partially fix these design flaws. They did this by increasing the span of the horizontal stabilizer, reshaping the rudder, and significantly widening the vertical tail. These crucial modifications were rolled out in early 1950. By this point, the aircraft had already logged about 100 flight hours during rigorous testing. Another major upgrade focused on passenger comfort. To eliminate an annoying vibration resonating through the cabin, the 3 blade propellers on the inboard engines were swapped out for 4 blade props. Eventually, these 4 blade props were fitted to all 4 engines. After these technical tweaks and upgrades, the Apollo was officially registered as a civilian airliner. On October 30th, 1950, the aircraft earned its certificate of airworthiness. It did come with a few restrictions, however. The paperwork cleared it to carry passengers. This was strictly for non-revenue flights. That meant they could not actually sell tickets. By that time, the Mamba turboprops were officially cleared to deliver 920 shaft horsepower on takeoff. The aircraft's maximum gross takeoff weight was capped at 45,000 pounds. On March 12th, 1951, the Apollo set off for Paris. This was the first in a series of test flights. These flights were required under their contract with the Ministry of Supply. The route ran from Bagenton in the UK Strait to Orly Airport in Paris. During the trip, the airliner cruised at 11,500 feet. The flight took just 86 minutes. To put that into perspective, it shaved a full hour off the standard British European Airways scheduled flight time from Birmingham to Paris. The return trip to Bagenton was even faster. Cruising at 12,000 feet, the airliner made it back in just 78 minutes. It seemed like a fantastic start, but plans for the next round of test flights had to be put on hold. Management decided to hold off until the testing program was fully completed. They also wanted to ensure a full commercial certificate of airworthiness was secured. As history would show, the aircraft never actually received that coveted document. In July 1951, it was fitted with more powerful, uprated Mark 504 engines. These produced 1,000 shaft horsepower on takeoff. However, late that same year, a major compressor failure grounded the airliner. It remained grounded until the spring of 1952. At that point, engineers swapped in new power plants with modified compressor blades. These updated engines, however, were slightly derated. They put out 970 shaft horsepower for takeoff. Back in 1950, the development team had already kicked off an aggressive marketing campaign. They were hoping to pitch the airliner to European carriers. To drum up interest from potential buyers, they organized several demo flights along experimental routes. Their sales pitch was highly detailed. The base price for a single airframe was set at £200,000 sterling. Their math assumed an annual utilization of 3,000 flight hours. This would allow the aircraft to fully pay for itself over 8 years of service. Based on these figures, the marketing team calculated the direct operating costs. A flight over a standard stage length of 260 miles would cost an airline £96.16 sterling. Unfortunately, those anticipated sales never materialized. Further testing kept exposing new flaws in both the airframe and its engines. Because of this, the sales team's enthusiasm quickly fizzled out. By 1952, it was painfully obvious that the Apollo had absolutely zero commercial prospects. So in June, management made the tough call to permanently cancel development of the airliner. At that point, construction on the second prototype was not even finished. Despite the project's cancellation, they decided to go ahead and complete the second aircraft anyway. Finally, on December 12, 1952, this airframe took to the skies for the first time. It was later handed over to the Royal Air Force. It made 2 more flights that December. After that, it returned to the factory to be fitted with additional equipment. It was not until September 1953 that the fully outfitted aircraft flew again. Both Apollo prototypes were funded by the British Ministry of Supply. The development and flight testing program finally came to an end. At that point, these experimental aircraft were handed over to the government. They were then sent to the Aeroplane and Armament Experimental Establishment at RAF Boscombe Down. The first prototype arrived at its new base on September 24, 1952. By that time, the aircraft already had a solid operational history. It had logged about 300 flight hours. The second prototype never received a civil registration. It was handed over to the military a bit later, on October 15, 1953. Over at Boscombe Down, the first aircraft was converted into a flying testbed. It was used to test the DECA radio navigation system. This system was brand new at the time. These intensive trials ran right up until April 1953. That is when the aircraft suffered a serious accident. After logging around 400 total landings, the landing gear struts failed under the stress and collapsed. To prevent a repeat of the incident, engineers quickly redesigned the landing gear on the second aircraft. As for the damaged first prototype, they decided not to even bother repairing it. In December 1954, it was simply dismantled. It was then returned to the manufacturer, Armstrong Whitworth. There, the remains of the airframe contributed to aviation research. They were used for further testing on metal fatigue. Meanwhile, the second Apollo had also arrived at the test center. It was slated for a series of general handling trials. As soon as that program wrapped up, the aircraft was transferred. It went to the prestigious Empire Test Pilot School at RAF Farnborough. In reality, the local test pilots were far from thrilled with the aircraft. The engines were notoriously unreliable and constantly ran rough. Because of these chronic technical issues, the airplane struggled during its entire 9-month stay at the school. From March to December 1954, it logged a dismal total of less than 20 flight hours. The second prototype made its final flight on December 14, 1954. After that, its flying career was officially over. The aircraft was handed over to the Structural Test Department. This department was part of the Royal Aircraft Establishment right there at Farnborough. The fuselage was submerged in a massive water tank. This was done for a rigorous series of pressurization tests. Looking at this troubled history, a fair question inevitably comes up. Could the Apollo have ever really competed against its main rival, the Vickers Viscount, if its engine issues had been resolved from the start? The reality is, just like its competitor, the Apollo was simply too small for what the market needed at the time. To have any real shot at success, it would have needed a much longer fuselage. A stretch like that might have also resolved the lingering stability and handling issues that plagued the aircraft. But valuable time had been lost, and the Viscount already had a massive head start. Plus, it is hard to shake the feeling that Armstrong Whitworth simply had other priorities. They were heavily tied up, fulfilling lucrative military contracts. All of this diverted the energy, resources, and momentum away from the Apollo project. Those exact elements were what was needed to make the airliner technically sound and commercially successful.